Okay, that's a different person who's speaking now on my Zoom, it sounds like. So welcome back, everyone. Hope everyone had a great summer. We're going to continue on with one of the most popular hard-hitting series on YouTube. Unfortunately, Kim couldn't make it today, but we're hoping to bring you, some really great talks this fall. We're really happy to have Felix Tintlenot to tell us about spatial economics for granular settings. And Jonathan is in the chat window if you have kind of clarifying questions, but everyone knows you should feel comfortable just treating this like an in-person seminar. So take it away, Felix.
Great. Thanks so much, George. Thanks so much to the organizers for inviting me to present this paper. And thanks a lot for the public service you're doing by creating sort of this space for this virtual trade and macro series, which I think is great. Today's work is joined with Jonathan Dingle, and we aim to make a methodological contribution in this paper to the quantitative spatial economics literature, which has developed powerful tools to study the effects of local economic shocks, such as changes to workplace employment or productivity, for example, through Amazon's proposed but later abandoned second headquarters in New York City, or to changes in land, housing, or residential amenities, for example, in studying what would be the best neighborhoods in Detroit to revitalize, or to changes in transportation costs, such as a new subway line in Berlin. So when studying these local economic shocks, the spatial linkages, so commuting, trade, local externalities, and other things, govern the incidence of these shocks. So the goal is sort of to have an empirically relevant general equilibrium model to perform these counterfactual policy exercises, as nicely stated in the handbook chapter by Redding and Rossi Hansberg. And this canonical framework economists have been working with has a continuum of agents, which has the convenient property that the observed shares of people making a particular choice is then also equal to the model probabilities, if you truly think sort of the world has a continuum of agents. So the starting point for this paper is for us to point out that the high resolution spatial settings that people have been studying are granular. So by that we mean that an individual decision maker is large relative to the economic outcome being examined, so that this sort of idiosyncratic shocks to individual decisions will not sort of wash out to the unit of observation sort of studied by the economists. For example, if you have fewer individuals, then the choice set faced by an individual of where to reside and where to work, you naturally sort of, it will not be the case that idiosyncratic decisions sort of would wash out in the aggregate as you would have with a continuum. So this generates a bunch of challenges for producing predictions in granular settings that go sort of through all parts of the analysis. So in the estimation part, you need to ask yourself the question, is an outcome really twice as probable because two people as opposed to one person sort of chose it? In the continuum setup, you would say yes, because you have this sort of linkage between observed shares and model probabilities, but with a finite set of agents, then of course not. And then the theory, now individual choices can affect local labor supply on land demand, and thereby affect the prices of labor and land. And then in the counterfactuals, now equilibrium outcomes may depend on individual idiosyncrasies. So in addition sort of to doing a comparison of means, you may actually also be interested on sort of how sensitive the change in the means is sort of to idiosyncratic noise. So broadly, sort of this talk is structured into two parts. So in the first part here, we'll still be working with the conventional continuum model. In fact, I'm going to start with a super brief review of how people have been computing counterfactuals in these continuum models. And then we sort of examine sort of two approaches of doing counterfactual analysis inside the continuum model, while applying this to sort of real-world data in New York City of local employment booms, in which we find that for 80 out of the 83 events, one of the popular methods, the so-called calibrated shares or exact head algebra method, sort of fails to make or makes worse predictions than a method estimated with only a single bilateral covariate being the commuting time. And we also show that sort of via Monte Carlo that sort of this granularity, which is sort of the only source of misspecification of the sort of continuum model, can sort of explain this discrepancy. And then in the second part of the talk, we're going to talk about the what we call the granular model, which will have the feature that wages and rents can sort of also depend on idiosyncratic shocks. So whereas you could sort of apply the continuum model to data with finitely many agents, if you take sort of a view that the data is a sample from the continuum, you're never going to get any price fluctuations from that, because if the data generating process is a continuum, then by construction, sort of these prices will be fixed and not depend on individual idiosyncrasies. So if you sort of want to then take seriously that you're operating in settings with relatively sort of a few agents, then you need sort of a granular model to also get these price fluctuations. And then finally, sort of we apply these methods to Amazon's proposed second headquarters in New York City. So maybe take a short break and take some clarifying questions, or push forward. I'll push forward then. Okay, so let me do this review. So of how people do counterfactual analysis in spatial economics models with a continuum of agents. And because this is sort of largely illustrative, so we here are going to just present the bare bones model and abstract from like richer interactions like consumption or production externalities. So here in this bare bones model, each location has a fixed productivity denoted by A, and a land endowment, which you can also think of sort of the housing stock denoted by T. There's a measure L individuals who each have 1 unit of labor supply and are hired by competitive firms producing a freely traded goods, which is differentiated by location of production. So this is sort of in the conventional Armington assumption. And individuals have Cobb-Douglas preferences over goods and land, where alpha is sort of the consumption share of land. And then they have idiosyncratic taste for pairs of residential and workplace locations. So nu K and I is individual, K is the residence, and N is the workplace. And then the other part of their indirect utility function here, so basically sort of their real income. So this is the labor income, the wage they would make in workplace N, divided by the rental price in residence K. Because of freely traded goods, the good price index here is common across location, and then delta Kn are the commuting frictions. And epsilon here, this parameter, is also known sort of as the commuting elasticity that sort of governs the importance of this sort of more fundamental part relative sort of to the idiosyncratic shock part. So very sort of standard and basic setup, and the equilibrium in this model is quite straightforward. It's sort of a set of wages and rents and labor allocation, such that the following three equations hold. So the labor allocation is equal to this term here on the right, which is the sort of the usual loaded share formula from the discrete choice problem. The good market has to clear. So this is the good supply of the good from location N, and this is the good demand. And good market clearing here also implies labor market clearing. And then finally, the land market has to clear. This is the land supply, and this is the land demand. And provided that this parametric restriction here holds, then we can apply the insights from the work by Allen, Arkulakis, and Lee to show that the equilibrium of this model is unique. So now let me tell you how one can do counterfactuals in this setting. So there are broadly sort of two different approaches that the literature choose between, of which sort of the second is way more common. So let me start with the first. We label this the covariance-based approach, which was, for example, chosen by the econometrica paper of Alford and co-authors of studying the effects of the Berlin Wall. In this approach, you parameterize the commuting friction delta Kn as a function of some observed covariates, for example, travel time. And then you do the usual thing, you estimate the model, and then compute the counterfactual outcomes at counterfactual values of either like productivity or commuting or something else. Now, a feature of this approach is that equation one, here the labor allocation, is generically not satisfied, perfectly satisfied under the estimated parameters, because here you can sort of take arbitrary data on labor allocation, and just with a set of workplace and resident fixed effects and a few sort of covariates, you're not going to be able here with the right-hand side to replicate any possible outcomes here on the left-hand side. Now, in their setting of alpha and al, it actually made sense to do this because they are only observing a sample of commuters. So what's here sort of on the left-hand side was just a sample, and it didn't need it to be perfectly fit. However, in most sort of other applications, people actually observe or researchers observe the population of commuters. So they're often more interested sort of to have this equation here from the model holding perfectly. And in that case, has been very popular to use the so-called calibrated chairs, or in trade, the exact height algebra approach, where sort of implicitly inferring combinations of the deep structural parameters by assuming sort of equation one is perfectly satisfied at the observed labor allocation and wages. With, for example, the feature that then if you have no people on a particular route, the only way to rationalize that is that the commuting frictions must have been infinite. And then you can compute counterfactual outcomes due to proportionate changes in either productivity, land, or commuting frictions without having even to know their initial levels. And as I mentioned earlier, we think of, or from going through the literature, this second approach is used far more frequently than the covariance-based approach. Felix, so now we're going to put both of these methods to test, sort of in what sort of is.
I think Durian wanted to ask a question.
Yes, great.
Yeah, I just don't know whether my microphone is working. So just, I don't know how important this is for what you're doing going forward, but just sort of to be clear here, the analogy is, say, with gravity equations for trade, which we're all super familiar with. In number one, we have sort of, we're estimating a gravity equation where we have bilateral distance, and we put in an error term which captures, all the deviations of what's the data generating process from, basically all the error in the misspecification of the model shows up in that error term. Whereas in the sort of approach 2, all the model misspecification in some sense is hidden by the fact that you're just shoving it into this delta Kn.
Yeah, or maybe you also have the error term, but you're sort of going to carry the error around as a structural error. Whereas in the former approach, you may or may not drop that error. Sort of, or in the former approach, you would drop sort of that error. So I think this will be crystal clear, like in 3 or 4 slides where exactly sort of that error shows up. Let me sort of do it in that context. Yeah, thanks. So let us first show you sort of, the empirical setting we're going to study. So we're going to look at commuting choices in New York City, which has 2.5 million people that both reside and work in New York City. And we're going to work with census tracts, which is sort of a standard level of aggregation, sort of these kind of commuting or like spatial studies, of which there are around 2,000 in New York City. So you have 4.5 million census tract pairs, because the choice set here is sort of the product of the number of residents and the number of workplace locations. So as you can see, so on average, like half a person per tract pair. So it's obvious that some of them must be 0. In fact, we find like 85% of these tract pairs have 0 commuters between them. And of those who have a positive number of commuters on them, actually 1/2 of the tract pairs just have 1 commuters on it, and then another close to 20% have 2 commuters, and so forth. Of course, a number of tract pairs, you have a lot of commuters on them. And I mean, given that this is partially a macro audience, you may be wondering, why do I have to pay attention to these small numbers? It turns out that more than 40% of the commuters in New York City actually make a commuting choice in a cell with less than 5 other individuals. So to the extent that we sort of are going to mismeasure the commuting frictions for for these tract pairs with few individuals on them, that actually is going to affect the commuting frictions for a lot of individuals in New York City. And another feature of why maybe it's problematic to just infer the commuting frictions directly just from the individual choices made in 1 year is that these data on the zeros don't seem to be particularly stable. So 44% of the tract pairs that had a positive flow in 2013 then became a 0 in 2014. So another way of cutting the data, analyzing the data, is if you want to predict the 2014 values of commuting, actually for most commuting pairs, it's better to take the predictions from a gravity model than to write forward the observed data just from 2013 into 2014. Okay, so that's sort of the setting we're dealing with. Yeah.
There's a lot more granularity than I'm used to thinking about. And so maybe you could sort of speak to what's the right level of granularity to, and why we should be so granular, right?
So I mean, it's not all that, census tract is a common unit of analysis, like in these sort of commuting studies, and then also in the broader economics literature. For example, I mean, all the work that Raj Chetting has been doing on income mobility and sort of how that varies across neighborhoods, that's all sort of at the census tract level. So, these issues still arise for sort of some of the counties, if you sort of aggregated the data to counties. And we're also going to do some aggregation here later to neighborhood tabulation areas, which are sort of 10 times larger than the census tracts, and show that the issues with the sort of calibrated chairs approach sort of persist even at this level of aggregation. And then finally,
Felix, sorry to interrupt. I had a similar reaction to George. I was surprised to see this granularity at the people or commuters level. Usually when we think about granularity and your motivation, you had firms, and I can understand why, Amazon is a big firm, shocks to the Amazon is going, or decisions of Amazon is going to affect the aggregate. Individual firms' markups depend on each other if they're large. Why does commuters? You're not, I suppose, suggesting that a shock to one commuter is going to affect the aggregate prices. So why are we? What's the motivation for looking at granularity at the individual person?
Well,
commuter.
I mean, you're going to see it in a moment, sort of when it comes to sort of the horse rates and the predictions, why this sort of is important. But here, I mean, what we're showing here, and I agree with you how macro often thinks about granularity, but here we show that even with homogeneous agents, you're going to have this notion of granularity that individual shocks sort of won't wash out in the aggregate, sort of for these choices, for these commuting choices. Yeah, so we're going to show it's going to matter. So
wait.
Yeah. Okay. So in order, so we are going to have two approaches to show that it matters. A, we're going to do a sort of a Monte Carlo in a second, and B, sort of we're going to do real world event studies. So, but for that, sort of we need sort of to quantify the model. So for the next 2 minutes, let me show you sort of how you sort of parameterize these models. So the housing consumption share, we just sort of take set to 24%. And the Armington elasticity we set to 4, just like some prior work in the literature. And L here for us is the number of employed individuals in New York City. So we are seeking values of the commuting frictions, the commuting elasticity, and then the residential fixed effect, and the workplace sort of productivity. And we sort of going to parameterize commuting friction in the following way. We think of them as consisting of an observed part. So for example, that's related to travel time, and an unobserved part. And that sort of will allow us sort of to speak to both methods. So the observed part, we calculate from Google Maps transit time. So we take here sort of a Beckerian view that each individual has a fixed number of hours per day that he or she can use either for working or commuting. So if you spend more time on the road or on the subway, then you will have less time to work. So here 8 we're going to set to 9 hours, and then sort of in the denominator from these 9 hours, sort of we subtract the time to travel to your workplace and the time to travel back from your workplace to the residence. So this sort of time sort of melts away of your work time in the commute, sort of to do sort of the trade analogy of the iceberg trade cost. So for the covariance-based approach, we take sort of, I mean, for illustrative purposes, the extreme sort of stand that this is sort of the only covariate and assume that lambda kn takes the 1. Of course, you could do other cases, have additional covariates, have like more broadly aggregated sort of fixed effects in here. That's all sort of feasible, but we'll show that you actually already do better. Sort of, you just say you have this single covariate as opposed to doing this other approach, with this sort of the calibrated chairs procedure, which will sort of assume that there is a sort of error term that's appropriately orthogonal to this, and sort of will carry this error term sort of forward through the entire analysis. So then with this, you can estimate the commuting elasticity. So if you take the covariance-based approach and you think the model is generated by, the data is generated by a commuting, a continuum model, but is only a sample, then a natural way to estimate the commuting elasticity here is via maximum likelihood, where this is the number of people making a particular workplace residence choice, and this is the conventional logit probability. Whereas in the for the calibrated chairs method, you could use sort of the commuting gravity equation and estimate, so after taking logs here, epsilon is the coefficient on this observed commuting cost part. And if you were assuming this moment condition here, then you can estimate this via PPMLE. It turns out that the first order conditions, when maximizing the maximum likelihood, also coincides with the first order conditions of this Poisson pseudo maximum likelihood. So both methods sort of will, in principle, like agree on the commuting elasticity, which we estimate to be around 8 in this setting. So now coming back to Doreen's question, so the disagreement here between these methods is sort of not because of epsilon, but really how sort of to handle this this error term lambda kn, whether to think of this as sort of something structural that you're sort of are carrying forward, or sort of not sort of include sort of this lambda kn in the analysis going forward as sort of in the covariance based approach.
Just one other point there. I mean, this orthogonality assumption, in some sense, is necessary to make this bottom thing work.
Yeah.
If I, for example, thought that the lambdas were correlated with something that I observe, then the way in which I would estimate the epsilon I would have to take that into account in estimating the epsilon. And that's kind of another potential wrinkle that you would have to think about.
Yes, I agree. I agree. So then we also would have disagreement on the epsilon, but here, I know, in order to minimize the moving parts, sort of we specify this way that that you could sort of in principle agree on the epsilon. I agree that you could make other choices, and then you may have also in disagreement on the epsilon. But going forward, epsilon is sort of not important for why the performance of these two approaches sort of differs, because it's the same. I agree. Thanks. Okay.
Felix, could I just clarify here?
Yes.
Maybe this is very trivial. For your log likelihood function, there's also a lambda at the background, right? You are really just writing down the likelihood function of the joint distribution of these lambdas. So are you just saying to the extent that if you're making the same parametric assumption about this lambda in the likelihood function?
Well, no, but this is the likelihood function of individual, I mean, coming from the individual choices, whereas here you already sort of did the sort of law of large numbers thing of saying, okay, this holds exactly. So you don't need that. It turns out if you think the data is a sample, then you don't need the lambda kn in order to write that likelihood function.
But what is the structural error interpretation in your log likelihood function approach there?
So here there is no structural error.
Just random error.
Yes,
just
exactly. Yeah. Well, there's, so I mean, sort of, these are all idiosyncratic. The only noise here is sampling noise, basically. So in this part.
I see.
So just sort of to close this, and thanks, Daniel. As to close this discussion, then sort of in the covariance-based approach, you could solve then for the for land and productivities using the estimated fixed effects here, the origin and destination fixed effect, and then sort of equations from the model, and they sort of can be uniquely recovered from these fixed effects. And in the calibrated shares procedure, you don't even need them because you sort of kind of use later the observed shares. So the only thing you're going to be using going forward is the epsilon, but of course, there are sort of implicitly some of these structural parameters under the hood in the calibrated shares procedure, and in particular, sort of going to be this error that you are only carrying around. Okay, so now let me show you the Monte Carlo. So the thought exercise here is that, okay, suppose the data generating process is the estimated covariance-based model for New York City in 2010. And then the event which I'm going to study is sort of a large increase in productivity of this location in 200 Fifth Avenue, which turned out to be the location where Tiffany consolidated its headquarters in and sort of led to this large local employment boom. So we're going to do 100 simulations of 2.5 million people, ex ante and ex post from the data generating process, and then apply both sort of the calibrated shares procedure and the covariance-based approach in order to try sort of to predict the model, so the commuting flows in response to that shock, wherein for both methods, we're going to increase the productivity in that location sort of to match the total employment increase in this simulated data. And sort of what this sort of AN increase in AN is made sort of differ by methods and their sort of simulation draw. And then the question is, does the procedure predict the change in the number of commuters coming from each residential tract working in this sort of treated location? And we have sort of two ways of evaluating this. The first is to sort of regress the observed changes on the predicted changes. So where we have sort of 2,160 observations or census tracts sort of per simulation. Where ideally you sort of would want to have a slope of 1 and an intercept of 0. Or alternatively, we can compute the forecast error or root mean squared errors for the observed versus predicted changes.
Felix, why is that the thing I want to look at? I mean, suppose I did a weighted regression. I just wanted to kind of know how well I predict the movements from Brooklyn to another popular place. I'm going to probably get that always right. I'm just not going to get like Brooklyn to the 7th floor of Stern's building right. So, at what level of aggregation do I want to be doing these regressions when we're in a really granular world? It's kind of, man, this really reminds me of the work that Rock Armentzer did a long time ago, where I really don't want to look at like these individual flows because I kind of don't really care that. Yeah.
Well, it's going to matter for these incidents of these shocks, right? Sort of. So I'm going to show you that later, sort of in the final part of the talk, how the incidence of the shocks is sort of affected, the calculation is affected by your estimates here. And then in a moment, I'm going to show you what you're going to get if you aggregate by a factor of 10. So,
okay. At this point, we're just looking at how well we predict these bilateral flows, which are just super granular, right?
Yeah, but again, this is not, I mean, we're not inventing sort of taking this level of aggregation, sort of, we're following sort of the literature here. And in fact, we are going to show you in a second. I mean, the Monte Carlo is sort of obvious, kind of has to be the case. There is one method that works. You should not use the other method. I mean, that's sort of the learning. It's not, we're not saying it's granular and it's hopeless. We're going to sort of show you here it's granular, so you should use method A and not method B.
Okay.
So let me start with the thing sort of that sort of should better work by construction. Otherwise, sort of we would have made a mistake because there was a data generating process. So the data generating process was a covariance-based method. So on average here in blue, across these 100 simulations, the intercept from these predictions is 0, and the slope is equal to 1, as you want it to be. Whereas you can see here in red, the calibrated shares procedure is totally off. So its slope is the median slope is close to 0 in these prediction regressions, and the intercept is sort of also moved. So what's going on? So this table here in the bottom, I think, is helpful. So we started with the baseline is to do this initial simulation exercise with 2.5 million individuals, just as we see them in the data in New York City. And now here, this is sort of the mean slope for the calibrated shares. This is the mean intercept. You can see if you have 25 million individuals while keeping sort of the number of the choice set the same, the predictions would improve of the calibrated shares, but not sort of be perfect. So if you go sort of 2 orders of magnitude higher, then you're really sort of close to nailing it with the calibrated shares. And sort of only like if you sort of increase by 3 orders of magnitude, then you sort of totally nailed it. There is essentially very sort of little granular noise if you had 2.5 billion people living in New York City, and then sort of using the calibrated shares on this sort of setting would just sort of be fine. Just here is showing that sort of the conclusions also kind of work with the RMSE. So now this was the Monte Carlo. Of course, in reality, other things may be going on. Actually, the calibrated shares may be picking up useful things, right? Sort of. So, for example, a lot of people, as Jonathan knows from having been a student there, sort of live in Columbia sort of dorms and work sort of in the university, Columbia University next door, and the single covariate sort of wouldn't pick this up, but the calibrated shares may be fitting sort of these shares. So, so in principle, so that's why we also need to look in real world sort of data and contrast these methods. So that's what we're going to do next. So
before you move forward, yeah. one more, I guess, question, comment.
Yeah.
Just, so, you know, I think about the covariance-based approach. Maybe I think about that I estimate a model, I check the fit of the model. If the model fits well, I say, okay, we're good to go, let's do a counterfactual. In the sort of shares-based thing, it's like I just basically force the model to fit the data by shoving everything into these wedges, and then I do the counterfactual. And one of these approaches may be more robust, not just to granularity, which you focus on here, but to sort of model misspecification, because you have this first step where you check the fit of the model. If I ran that first gravity equation and the fit sucked, and I started to do a counterfactual, people would laugh me out of town. But I can do that wedges thing even if the fit sucks, because nobody ever sees that the fit sucks. And in some sense, your point here about granularity is you could make it about any kind of model misspecification.
Yeah, I agree with that. I agree with that. Yeah. Just sort of to try maybe to balance things out, there is this sort of, I mean, what are we maybe missing with the covariates, right? So we may be missing the covariates we don't include. All right, sort of so they're good. It may also be pick up useful things. But that's sort of what we try to evaluate sort of next. So let me now show you this with the in a real world data or
Felix, I just have a very quick question related to what Dorian was asking you. Can you give us some guidance about, for instance, in your first step doing the covariance-based model, what type of just ratio test statistics or what type of pseudo R-square kind of diagnosis tools that we can rely on to say, up to this level, then we could have potential confidence in terms of thinking about that.
Right. I mean, it's something that Jonathan and I are still sort of, thinking about. But I mean, I think this Monte Carlo here provides a bit of illustration, right? Sort of. So if you sort of had 100 times as much data, so basically like 50 individuals per choice in our setting, as opposed to a half an individual per possible choice, then this would work fine. And but that's just like a simple heuristic that we sort of only sort of tested on New York City data. If you wanted to spend more time on it, like checking, probably the right thing to do is to run exactly that Monte Carlo in your study, right? Sort of. So try if you want to do calibrated chairs. Well, do a version where you parameterize the frictions, you simulate the data, and then try to do the model predictions for the calibrated chairs. And if you're going to sort of fail this Monte Carlo test, you should probably not use it. But that's sort of more time intensive than the heuristic.
Felix, I had one question before we leave this slide, which is the last table is very nice. That's kind of averaging over these distributions that you show above, right? To kind of look
exactly. That's correct. Yeah.
We're losing a little bit because your covariates calibrated.
So I'm only showing
have a lot of a fair distribution to it, particularly on the intercept, and so I kind of seems like we're missing one piece of information, which is just like
maybe we should add the covariance based thing. It was working very well, so we didn't want to show all the same numbers, but we should. But point taken. We could show you here the same below also for the covariance based. Thanks. Okay, great. So now let's show you this on based on real world event studies. So concretely, we're going to look at 83 tract level employment booms. We define sort of as an employment change in a workplace tract of at least 12.5% in New York City between 2010 and 2012. Furthermore, require that this census tract actually was sort of a suitable workplace to begin with, so there were at least 400 people working in this location before the employment growth. And so we can treat these as 83 events, and then sort of raise the productivity in the tract sort of to match the observed change in employment with sort of both sort of counterfactual methods, the calibrated chairs or the covariance-based one. And again, ask the question, does the model predict the changes in bilateral commuting flows to that destination? And again, we're going to sort of regress the observed changes on the predicted changes, and the target is sort of, ideally you would want to have a slope of 1, intercept of 0. So again, the fit of these methods varies across these 83 events. That's why we have a distribution here. But the message is sort of similar as from the Monte Carlo. So if you go, if you start with the covariance-based approach in blue, the covariance-based approach actually can handle this granular data quite well, right? So like the median, I think, is like 0.97 of the slope, so it's very sort of close to 1. and the intercept is close to 0. Whereas here the slope of the calibrated shares procedure, the median level of that across these 83 events is actually a small negative number, meaning that the predictions from the calibrated shares procedure are sort of weakly negatively correlated with the observed changes in the data. And if you use this sort of forecast error as an alternative metric, then 80 out of 83%, 80 out of 83 events, the covariance-based method forecast error is less than the calibrated shares forecast error. So one of the things that sort of already came up, so George asked this question earlier, what happens if you aggregate, right? So and sometimes for a long time we just always pushed at this against this because we say, well, I mean, you don't have to, you just use the covariance base. But then, of course, I mean, I don't know, people ask us this question over again, so we say, okay, let's just do it. So we aggregate the predictions to the neighborhood tabulation area level, which only 2/100 of, so it's like 10 times as large. And when you do this, the covariance-based sort of approach is still sort of fine, and the calibrated shares prediction do better, but they sort of still do worse, sort of using both metrics, sort of the slope or this ratio of the forecast error. So I think now it's like in 70 out of the 83 events that the forecast error is lower in the covariance-based than in the calibrated shares procedure. And sort of the loss here of sort of doing all of this is, of course, your predictions sort of get less fine. And some other things you could do is you could sort of pool the data initially because of this sort of year-to-year fluctuations. You maybe sort of do take 3-year averages. Again, this helps the calibrated shares procedure a bit, but it doesn't overturn the overall conclusions. And if we sort of shut off the extensive marginal response in the covariance-based procedure, so that the comparison is only sort of between intensive marginal responses, still the covariance-based procedure does a better job. So it's not all coming here from the extensive margin. So with this, in my last 15 minutes or so, let me now come to the second part of the talk, where we're going to take granularity even more serious, because here now, while you could sort of do all of this so far with the continuum model, you wouldn't get like fluctuations in prices from it, but prices, of course, are something that we as economists care about. So we think we should sort of also be transparent about that fluctuations in prices, and then consequently in the prediction, in the fluctuations in the predictions that we make, that's just coming from idiosyncrasies. And for that, sort of you need sort of a granular model with a finite number of individuals. So we'll try to stay here as close as possible to the continuum model, but just have a finite number of or integer number of individuals. In the limit, and I'll show you the details in a moment, the model is the standard quantitative spatial model. And when we're starting on this, we were faced sort of with the following problem. So we first thought, okay, maybe the right way to model this is that individuals are fully rational, and they go over all possible allocations of individuals to census tract pairs, and then calculate the wages and rents you would get for each of these allocations, and also put some kind of probability to each of these allocations, where this probability is sort of, I mean, some kind of gigantic fixed point. However, we quickly realized that this is not going to work because there are just too many possible allocations of individuals to census tract pairs. So just to put like a small numeric example, if you had 10 individuals and 4 tracts, so 16 tract pairs, and there are more than 1 million ways to allocate these 10 individuals to these 16 tract pairs. So when we try to calculate what that number would be for New York City with 2.5 million people and 4.5 million tract pairs, like the computer couldn't do it because it ran into some sort of overflow problem. So this is sort of not going to work. So we're going to have to sort of do something else. I'm going to show you in a moment sort of what we're going to do. And then the other sort of implication is that now, because you simulate individuals sort of for like the deep structural parameters, technology, land, and commuting costs, you're actually now going to get a distribution of outcomes just sort of from these idiosyncratic draws. So now let me do this a bit more rigorous. So I can go somewhat quick on this because we try to stay very close to the continuum model that you already saw. So I'm going to highlight the differences. So the commonality is each location has a productivity A and land endowment T. Now we're going to have a finite number of individuals I, where each individual is endowed with L over I units of labor. The reason we do this is that if you can then vary I, and L aggregate labor always stays constant, right? So we're not sort of doing anything to the aggregate labor land ratio as we sort of change I. And again, it's Armington. And then the second, same kind of preferences before in principle. The second main difference is that now workers sort of have to form beliefs about what these rents and wages are. And we assume that these are common point mass beliefs. So that seems strong. I'll explain in a moment and show you sort of, what goes right or wrong. So it's just to explain what that is. So they have some beliefs with 100% probability. They think sort of, okay, it's going to be a particular rent in a location. And with 100% probability, they think sort of that the wage in location N takes a particular value. And for now, we do things sort of with arbitrary beliefs, but we're going to discipline in them in the moment. They can be arbitrary, but they have to be point mass beliefs. And they also know sort of the idiosyncratic preferences, but not the preferences of the other guys. Here we're going to sort of make a timing assumption that would have no consequence if you had a continuum, but sort of matters if you have finitely many agents. Workers first sort of choose the workplace residence pair to maximize their utility using sort of these beliefs. Then they are locked into the location, and then so they are sort of locked into the location. Basically, like a little trade equilibrium gets realized. So given the labor allocation, trade equilibrium is a set of wages and land prices that clears all markets. And of course, these realized wages and rents, they may differ sort of from these initial beliefs. So then the bigger sort of overall equilibrium in this model, what we call the granular commuting equilibrium, is a labor allocation, wages, and rents, such that the labor allocation results from I independent draws from this logit probability function over here. And the wages and rents are at trade equilibrium given this labor allocation. And part of the conditions sort of this equilibrium are sort of also these point mass beliefs. So let me, so far this works for arbitrary point mass beliefs. So let me discipline those a bit more. This we're going to do here. Basically, as you take I to infinite, we're going to go back to this commuting gravity equation with sort of these wage and rent beliefs in it. So we're going to be working with so-called continuum case rational expectations, which are essentially the which would be the wages and rents if the model had a continuum of agents. So then as a result, if the individual point mass beliefs are continuum case rational expectations, then the granular models equilibrium quantities and prices coincide with those of the continuum model when you set let I go to infinite. So to say this in slightly different words, they basically they know the T's, they know the A's, they know the commuting frictions, and then they solve the continuum model, and they take sort of those wages and rents as their beliefs. That's sort of how your beliefs there.
That kind of reminds me of the sound of that bank card equilibrium in IO.
Yes, absolutely. Yeah, no, exactly. So it has some similarities to that sort of in IO or maybe in macro, like, I mean, in some way, Crustle-Smith, where you just say, okay, you just only need to know the mean, it has some analogy to that. Now, the whole thing, okay, so before I go to evaluating this, you just say that essentially estimation here is the same as before. You can do maximum likelihood, just that you have the beliefs in here, but then from these fixed effects, you're gonna back out later the workplace productivity and the land. And it turns out that the parametrization is exactly the same as in the covariance-based continuum model. So for the granular model, the T's, the A's, and the epsilon are going to be identical to those from the covariance-based continuum model. So always, of course, coming from Chicago, like deviating from rationality is like a big step, and people get like nervous when you sort of do that. So we need to sort of evaluate that. We evaluate this by sort of calculating sort of the exposed regrets. So naturally, like the realized equilibrium wages and rents will differ from the beliefs, right? So okay, George went to Rochester and he thought he would like earn a certain wage there. And then depending on how many students showed up, like his wage, realized wage actually was like a little below or above of what I expected. But even if his realized wage was below, it doesn't mean like that George really has a lot of regret, because he may not switch, right? Because he also sort of take into account his idiosyncratic preference draw. So we calculate sort of regret as sort of the additional income we would have to give you, so that at the realized wages and rents, you would be willing to stay as opposed to sort of switch to another location, which sort of we don't allow you to, because we said you are sort of locked into that location based on your beliefs. It turns out that this is quantitatively quite modest. So first, like 96% of agents here would not want to switch. And those who would want to switch, conditional on switching, like the median exposed regret is only like 0.7%, and I think the mean is around 1%. So given like the gigantic like computational simplification these sort of point mass beliefs deliver, we think actually sort of these small mistakes agents make here are quite palatable. So much time, not much. Let me push. So now so George, do you have 2 minutes, 3 minutes? How much do you have?
Take 5 minutes. It's okay, Felix. Okay. I'm not as tough as Kim.
Okay, thanks. Thanks for your patience, and I apologize for
that's okay.
Over a bit.
Okay.
Oh,
I slowed you down before.
Oh, no, but this was good. This was what to expect. These questions. So now, why do we have to go through this machinery of this granular model? So now I'm sort of trying to show you sort of where it shines a bit. So from that, basically, you can now start calculating like the uncertainty associated with your predictions that's sort of coming from granularity or just sort of sampling of a finite number of individuals as opposed to having a true continuum. In terms of the means, the covariance-based continuum model actually gonna give sort of the same quantity as the granular model sort of would give you like an expectation on average. Because the prices are like a nonlinear transformation, this doesn't hold exactly for prices, but in practice, we find again the prices of the covariance-based model and the continuum covariance-based model and the granular model to be quite similar. But now the covariance-based model can also sort of speak to like second order moments, maybe the fluctuations of these things. So we kind of suggest that when making some counterfactual predictions for, let's say, the number change in residence in K, some residence location K, people also sort of give us a sense of sort of the confidence interval that they get just from internalizing sampling noise. So one way to do this is just via simulations, just simulate the granular model a bunch of times into this counterfactual. It turns out you actually can, for predictions in quantities, just calculate this based on things you normally get out of your model, your standard continuum model. And we find in most settings, these approximations are very good. I don't want you to get lost in the math. Let me just sort of point to some terms. So you can basically calculate the confidence interval for these predicted changes just using the counterfactual probabilities of people sort of residing in that location, and then sort of taking, if you want to get the 90% confidence interval, just sort of taking the mean difference plus minus sort of 1.6 times this term. For prices, that won't be quite as simple because the continuum model won't give you any fluctuation in prices. So you have to sort of solve the granular model to get that. Okay, so last minute, let me just show Amazon HQ2. I have to like hurry up. So the event data got abundant, but they wanted to put this second headquarter here, sort of in Queens, in Long Island City. You can see that the predictions, the mean predictions from the covariance-based model are sort of kind of spatially coherent and smooth. Neighborhoods close to Long Island City would be sort of more affected in terms of change in residence. As for the calibrated chairs, it's kind of idiosyncratic and all over the place. Some large changes like further away. It turns out if you sort of put the initial data back next to it, that, namely the number of residents working in the treated tract before the event, that is an extremely good predictor of the counterfactual predictions of the calibrated chairs. This looks like kind of the same map, but with just different units, and these are sort of residents work at the treated tract. So whereas like both procedures actually sort of agree on the change. So this is then for rents. This will carry forward into rents. Both procedures agree on where the workers are coming from in terms of what sort of neighborhoods lose employment. That is sort of, I mean, taking roughly proportional to the initial number, and that's kind of the same between the covariates and the calibrated chairs. So let me sort of just maybe finish here. many of the mean changes are actually not, for this large event, are not significant when you take into account the sort of granular noise. So like when we calculate like the 95th and the 5th percentile in the change in residence from our granular simulation, or using the approximation, very similar, then they always sort of include 0, this interval. So sort of none of them, even though this was a big event, none of the changes in residence are really significant. For the changes in number of workers by location, some are significant for the locations that lost more than 250 workers, but this only like around 43 or so of them. And then for those, the changes in wages and real wages are also significant, whereas the changes in rent are all insignificant. And that is sort of, even though on an assumption that you knew your parameters perfectly, just sort of sampling noise generates these big fluctuations. So I'm way over time. So let me thank you for all the great comments. Happy to continue the discussion now afterwards. Thank you.
Great. Thanks, Felix. We have a few minutes, and it was totally fine to go a little bit extra. You had granular comments. So we'll kind of open it up, and anyone just sort of jump in and have at it.
Felix, I still this is really heavy burden work at the end, in terms of calculating this equilibrium. I still trying to get a sense of reconcile your earlier half with the later half, because it's still back to what Dorian was asking. I feel like your earlier point is really not that much related to granular. The idea is that the granularity, you have smaller units where you have less observations per cell, makes this mistake by interpreting sampling errors to this persistent structural errors to be more severe.
Yeah.
But that's a very general point you are making here early on, which is, no matter whenever you do that, from a cross-section data perspective, whenever you start to interpret the sampling error as structural error and you try to incorporate the structural error for your counterfactual analysis, you're going to make a mistake. So just been wondering, like, whether this kind of second half you were doing, what more you could potentially do, maybe just to kind of like, either you can use that to kind of maybe highlight your point, or just to think about to what extent we could be wrong. I'm trying to still digest, like, what role is the second half, that pretty complicated, heavy burden computational exercise you guys were doing is trying to achieve, given what you first told us.
Yeah. So I mean, let me slightly alter your initial statement. So as sort of our initial discussion, I think revealed, like, the big difference is sort of how to treat sort of the structural error, right? So what is a structural error? Could be a bunch of things, including sort of sampling error. In this setting, kind of, we show that sampling error is enough to mess up sort of the sort of calibrated chairs thing. And then we sort of study other implication of the sampling error in the second half, namely that then you also just the comparison of means. Once you take serious that you have sampling error, then we shouldn't just be comparing means. We actually kind of should be comparing distributions, right? Sort of ex ante distributions, exposed distributions, or even if you say ex ante is realized, then you do have for sure an exposed distribution. So that's sort of what we try to characterize here. And I mean, once you make the continuum case rational expectation choice, and you're fine with that, the computational burden is not that large. Maybe Jonathan remembers the statistics, but it doesn't take a lot of time to do these counterfactuals and sort of characterize it. But I'm open to suggestions what else to do in that second part. But we wanted to get sort of the why do we expose you to that second part? Because we think, hey, we want to characterize the distribution of the outcomes, and you could get distributions from the continuum model if you take a sampling point of view, but you're never going to get a distribution in prices. And we think as economists, prices are important. So then in order to get like fluctuations in prices, then you sort of need this granular model. So
yeah, I'll jump in just on the computational burden is not so bad, right? So a totally different way to frame the talk is like, one part of it was about getting the parameters right. And then the second half of your question was like, okay, well, once I've got the parameters of the model, why should I quantify this economic uncertainty? It's not statistical uncertainty about the parameters, but it's, economic uncertainty about distributions that are induced by individual idiosyncrasies. And so we've set things up intentionally so that how you estimate the parameters is the same as if you believed there was a continuum. So there's no additional estimation burden. So it's like a question about what's the burden of computing these counterfactuals. And if you choose your language carefully, you can simulate multinomial distributions to take draws extremely quickly. So that's not the burden. And then these models where you're, a standard trade model or standard commuting model like this is a contraction mapping. And so that's very fast as well. So I don't think you should be, it's not a big burden to solve a trade model 10,000 times with just 10,000 different draws of the labor allocation. So it can be done in a matter of hours. It's not a huge deal. I mean, maybe the notation made it look bad, but it's actually very computationally friendly, I'd say.
Hi guys, on this issue on the computational burdensome. So if you fix the idiosyncratic shocks, if you keep them fixed, one realization, then do you really need to solve this approximated equilibrium, or you assume that the agents are believed like it's the continuum model, or why is it so hard to solve the actual equilibrium? Is there multiple equilibrium? Fixing the draws. Is there any additional source of multiple equilibrium, or
there doesn't?
The number of unknowns that you're solving is the same as in a continuous model. You're solving a wage and a rental rate in each location. The idiosyncratic draws are fixed at this point. So why I didn't understand why you need to make this assumption that the agents believe like that the wages and rental rates are coming from the continuous model. I did.
Well, because they select into a particular residence workplace pair, and that selection depends on the prices, and the prices depend on the allocation, and there are just too many allocations to enumerate all of them.
So you're saying that there's multiple equilibrium potentially.
No,
if you solve like the true Walrasian equilibrium,
yes.
There's multiple equilibrium.
So there's a unique trade equilibrium, but even like it's like infeasible to do this sort of. You can't even say it's multiple. It's just simply infeasible to do this enumeration of. I form some beliefs of probabilities associated with each possible allocation of people, and then calculate the wages and rents associated with each allocation.
So I've got 2.5 million people, and I've got 4.5 million potential choices. Okay, fix everybody else's decision. Labor demand slopes downward. So if I change my decision, I change the wage. Labor supply is fixed, but if I bring more income to a residence, I bid up the housing price. And so the question is, this is a game with 2.5 million agents. Am I playing best response against all, there's 4.5 million deviations for me to consider, and then we have to evaluate that for each of the 2.5 million agents. So just find it. It's not about the multiplicity of like Nash equilibrium, that game. I think it's just finding it is a combinatorial nightmare.
I see, but every agent doesn't care about what they only care about the wages and rental rates. Yes. They don't care about the idiosyncratic decisions. So I guess a vector of wages and rental rates. I solve all the allocations. That's like individual by individual, and then I'm just isn't there a way to update that vector without having to rely on this approximation?
So
I think Ariel we're right. This is still a large scale game because the counterpart to that is like a Kuno game. In Kuno, you only also care about the aggregate, but that's fundamentally still a game. It's just a very large scale game that you do need approximation, which I think you are doing the kind of similar things like the oblivious equilibrium, which is you're essentially averaging over all the potential equilibria, and given these random noises realization, you're averaging over all the potential equilibria given their potential chance of appearing. So that's the very similar counterpart to the oblivious equilibrium, I think.
Yeah, just to add on, what we are doing is much simpler than what you're suggesting, right? So by taking the continuum case rational expectations, you don't have to solve for that fixed point, right?
In oblivious equilibrium, you don't have to solve that either.
Yeah, exactly.
They also show it in the continuum it converges to Hoppenheim.
Yeah,
so very much
Danny, I agree
similar.
100%. Sorry, I was just responding to Ariel, but I agree 100% with the analogy to the oblivious equilibrium.
So there was a question in the chat window too. I don't know if Vincent wanted to say it out loud or if it's kind of a technical question. So
yeah, I just wanted to ask. So I mean, obviously, for the as I tends to infinity for your granular equilibrium to converge to the continuous case, you want the idiosyncratic shocks to be distributed Fréchet or Gumbel. I don't know. It depends if you take the log. But I guess in principle, you could make the distribution of the idiosyncratic shocks be whatever you wanted, and then still solve the model. I don't know then what beliefs you would use, but maybe because Fréchet is not such a good. I mean, the main reason I thought you use Fréchet is because it gives you this very nice probability, but maybe that's not actually what people's idiosyncratic shocks look like.
Yeah, I'd say we followed the literature in doing plain vanilla Logit or Fréchet, but the vast majority of the issues we've raised here about, finite number of agents versus continuum model would apply if you gave me a different distribution that induced those probabilities. And to the extent that once you've got an expression for those probabilities, you want to run our granular model, yeah, you just simulate draws from that probability distribution, that multinomial distribution, it's no problem. The Logit or Fréchet is just standard in the literature, and I guess has that nice closed form expression, so it's very fast to compute. But there's no particular reason why the idiosyncratic errors have to take that form. You can imagine richer discrete choice models with different patterns of substitution if you wanted.
Yeah, thanks.
great. Anyone else? Okay, Sam.
Yeah, this is just kind of trying to connect the first part of your paper to sort of things about the multinomial distribution. And it's a little bit out of context, but there, I just remember from as graduate student, when you can use like a chi-squared distribution for kind of summing up the cells, and it'd be kind of cool to connect what you're doing to that, where they sort of say, oh, you should have at least an expected number of 5 landing in each bin to be able to be kind of on a good footing. And I'm sure that's very super hand wavy, but still, that's kind of a nice way to think about it. I wonder if you could relate your findings to, well, we need as long as you have at least 5 in each cell, 5 people making any decision that you're thinking about, then it's fine. Or maybe it's 100, or maybe it's 2 or something. That's kind of a nice metric, I think.
That's a great comment. Yeah, we'll look into that.
Yeah, we cite that literature a little bit in the context of the proposed approximation for the granular model. So when we said like you can use the binomial approximation instead of doing the simulation repeatedly, and I started going down that like biostatistics literature, and one rule of thumb is like 10. So you need an expected value of 10. Mm-hmm. Then there seem to be contrasting takes on whether that's the right rule of thumb and et cetera. But so we kind of invoke that in terms of talking about when is our approximation for the granular uncertainty appropriate. And it kind of lines up with the Monte Carlo, I suppose, in the sense of in New York City, we have half a person per cell. And we showed in that Monte Carlo that if you had like 2 orders of magnitude more data, you'd be okay. That'd be like, 50.
Yeah,
people
50
per
looks
cell.
pretty good. So yeah,
Yeah.
so that's like 100 times more. Okay,
Yeah.
yes, it's kind of in the right ballpark.
I mean, one thing that I would point out is rather than having to provide this rule of thumb, there's nothing specific to, like, whenever someone does exact hat algebra, they could run this Monte Carlo, because all this Monte Carlo is a test of the finite sample behavior, the finite sample properties of your counterfactual procedure, right? So this is basically assume, a simple DGP. So like the simple DGP could be your trade model where you only put in distance as the only trade cost covariate, and then say generate data from that model and then run exact hat algebra. Do you recover the parameters correctly? And if you can't, then you should say, I've got a very data hungry procedure because it fits every bilateral trade flow. And if I fail that Monte Carlo, it says like, I've zoomed in if I'm doing this on, lots of flows with lots of countries or doing it sectoral level, stuff like that. So people ask us for rule of thumb cutoffs, but at least one thing you can do if you're going to do calibrated shares, if you're going to do exact hat algebra, is just Monte Carlo your own procedure to explore its finite sample properties and show it's well behaved.
But also ask a very minor point related to this. If I have a panel data, for instance, if I have 2 periods of data on these cross-sectional distribution of stuff, would that add more of my ability? For instance, I could test if I back out these structural error terms over time for 2 periods, I could test their serial correlation, right? Or something like whether these are ID over time. That might actually also give a hint about in which word that we should treat these things more seriously.
Absolutely. No, that's a great point. So we try to explore that a little bit in the descriptives. Just showing that they're not super persistent, but in terms of suggestion of what people should be doing, I think it's a great point.
Yeah,
Jonathan, I think you unmuted yourself. So
time aggregation is a race between, do you think that the parameters are fixed? So it kind of depends on if you were doing 1 year and the next, fair enough, then you hope that there wasn't a big shock. And so you're basically seeing the outcome twice, and that gives you a power advantage. If you were, in some of these settings where people are doing this, so the trade data is usually annual, and that's probably very helpful. Sometimes people are working with a single cross section. The Berlin Wall paper is like data for something in 1930, and then 2 decades later. And if parameters have changed over time, then that's. But I think that's a good discussion to have, because usually exact hat algebra is like rationalize a single cross section perfectly and then do the counterfactual. And now it's like, well, if I've got 2 cross sections of data, how do I use that to evaluate model fit? I think that's a really good conversation to have.
Okay, well, let's turn it off.